Good morning, everyone. I hope that you're having a great week so far. What we're going to be looking at today is the second part of the Compton effect. And if you had downloaded the rest of the story, part 2, the note package, prior to this week, you would not have pages 21 and 22 in the handout. They've just been added in the past couple of days. So this is on page 21 of the lesson handout. And we're just going to extend what we learned last time and go a little bit further with the Compton effect. On Monday, what we learned is that during the Compton effect, you have a photon that's scattered by a free electron, and the photon transfers some of its energy and some of its momentum to the electron. The main thing that I want to focus on today is if the photon loses energy in the scattering, then its wavelength must increase. Longer wavelength photons have less energy. And Compton was able to come up with a relationship between the change in the wavelength of the photon and the angle that the photon is scattered at. So when you take a look at this diagram, and there's a similar one in your textbook, but this one I like a little bit better. When you take a look at this diagram, the photon to begin with has more energy than the photon afterwards, and you can see that the wavelength is stretched out more afterwards. In this formula, which is called the Compton shift formula, the change in the wavelength of the photon is equal to h over the mass of the electron multiplied by the speed of light multiplied by 1 minus cosine of theta, where theta is the angle that the photon is scattered at. And we're just going to go through one example today using that formula. X-ray photons of a wavelength 0.28 nanometers are Compton scattered by free electrons, and the photons are scattered at an angle of 78 degrees. What's the wavelength of the scattered photons? So what we can do to begin with is find the wavelength shift, or the change in the wavelength of the photon, by using the formula h over mc multiplied by 1 minus cosine of theta. So the change in the wavelength will be equal to Planck's constant. We have to use standard units here. Over the mass of the electron, 9.11 multiplied by 10 to the negative 31 kilograms, multiplied by the speed of light, 3 multiplied by 10 to the 8 meters per second. And then we have to multiply that by 1 minus cosine of the angle that the photon is scattered at. So 6.63 multiplied by 10 to the negative 34 divided by the mass of the electron, and also divided by the speed of light. You could have said divided by and then had a set of brackets where you multiply the mass of the electron and the speed of light together, but I've chosen to just divide by each of them separately, which mathematically is the same thing. Now I'm going to multiply by 1 minus the cosine of 78 degrees. I'm going to make sure I'm in degree mode. And what I get for the change in the wavelength is 1.92 times 10 to the negative 12. So my change in the wavelength is 1.92 multiplied by 10 to the negative 12 meters. You do have to remember something, and it's that the final wavelength in the Compton effect is always greater than the initial wavelength, which means to find the final wavelength, we're going to take the initial wavelength, which was 0.28 nanometers, and add the change in the wavelength, because that's how much the wavelength increases by. And that will be the answer. So the final wavelength is the change in the wavelength added to the initial wavelength, and that gives us 2.82 multiplied by 10 to the negative 10 meters. And that's the answer to part A of this question. When we take a look at part B, it says, what is the initial and final energy of the photon? So we're going to use E equals hc over lambda to calculate the energy of the photon to begin with and the energy of the photon afterwards. So the initial energy will be equal to hc over the original wavelength, which was 0.28 nanometers. The final energy is hc over the final wavelength, which I believe was 2.82 multiplied by 10 to the negative 10 meters. I'm going to calculate the final energy first, simply because I still have that wavelength on my calculator. 6.63 multiplied by 10 to the negative 34 multiplied by the speed of light, which is 3 times 10 to the 8, divided by my wavelength, and I get 7.055 times 10 to the negative 16 joules. And before I go on, I'm going to choose to store that in my calculator as A for after. Now I'm going to calculate the energy that the photon had before. That is Planck's constant, 6.63 multiplied by 10 to the negative 34 times the speed of light divided by the initial wavelength, the wavelength before, which was 0.28 nanometers. And I'm going to store that as B for before, and it's 7.104 multiplied by 10 to the negative 16 joules. All right, let's take a look at C. What is the kinetic energy of the scattered electrons? Well, if we go back and take a look at the two energies we calculated here for the photon had 7.104 multiplied by 10 to the negative 16 joules of energy before it collided with the electron. And after the photon collided with the photon had only 7.055 times 10 to the negative 16 joules. It's that loss in energy that goes into the kinetic energy of the electron. In other words, we're talking about conservation of energy here. We're talking about energy before the collision and energy after the collision being equal. Before the collision, there is only a photon energy. After the collision, there is a photon energy and there is a kinetic energy of the electron. And we know both of these photon energies. This was the 7.104 multiplied by 10 to the negative 16 joules. This is the 7.055 multiplied by 10 to the negative 16 joules. So we can solve this equation to determine the kinetic energy of the electron. And I knew where this question was going, which was why I saved both of those numbers in my calculator. I wanted to carry all of my decimals. So I'm going to take the energy before and subtract the energy after, and we get 4.84 multiplied by 10 to the negative 18 joules. And that's the kinetic energy that the electron is scattered with. And the last question that we were asked to answer, what is the speed of the scattered electrons? Well, now that we know the kinetic energy of the scattered electrons, we can set that energy equal to 1/2 mv squared and solve for the speed. A calculation we've done dozens and dozens of times. The kinetic energy of the scattered electrons is that 4.84 multiplied by 10 to the negative 18 joules. So if we take that energy and multiply by 2, and then divide by the mass of the electron, then take the square root of the answer, we're done. The answer is 3.26 multiplied by 10 to the 6 meters per second. That's it for the lesson. There are 6 problems you can work on. There is a 7th challenge problem, I believe. And these problems are on page 22 of your lesson handout. Tomorrow is a Google Meet day, so if you have any problems, show up, ask your questions, and I can help you out. In the meantime, remember that you can always send me an email at any time if you have questions, and as soon as I get that email, I will reply back to you. There's nothing going on Friday, and there's nothing going on Monday. We're dealing here with a 4-day long weekend for you. Have a wonderful rest of the day, you guys, and if I don't talk to you tomorrow, have a fantastic weekend, and take care of yourselves, and we will talk to you soon.